In this lecture, let us talk about demodulation of AM signal with carrier. So, in the last class, we were talking about amplitude modulation. In the last couple of lectures. So, we looked at the important properties of the amplitude modulated signal. We discussed the time domain waveform, and we also looked at the frequency domain spectrum. Okay, and then now in this class, let us talk about demodulation of AM signal with carrier. Okay, and one important point that we said in the last lecture was the envelope of the resulted signal follows the message waveform. The envelope is denoted by E of t. It follows the message waveform M of t, directly proportional to M of t. Okay. This is of course a useful property, and this could be done by inserting the carrier in the transmitted signal. Okay, in this case basically the modulation index mu should be less than 100%. That means what? Less than 1. Mu must be less than 1. If mu becomes more than 1, essentially the shape following property will not be there, and we will not be able to demodulate the signal, and we will not be able to have the advantage of using simple demodulator. Okay, and the demodulator structure was extremely simple if modulation index is less than 1. Okay, your M of t, magnitude of M of t must be less than 1. This is very important condition. So, in this lecture we will discuss the demodulation of such a AM modulated signal, something called envelope detector. It is a very simple circuit. Okay, so you take a simple diode followed by a resistor in parallel, and then parallel with a capacitor C. This is your output and this is your input. Okay, so the input is a modulated signal x of t, and the output, let me call z of t. This is the proportional to your message signal M of t, and the diode conducts only in the positive half cycles of the carrier. Okay, the diode does not always conduct. Okay, therefore you have a diode, you have a suitable value of resistor R and suitable value of the capacitor C. When I say suitable value R and suitable value C, that means you cannot choose the R value and C value arbitrarily. Based on the certain conditions, you should choose this R and C, because R and C will determine the demodulated signal. Okay, so input is the modulated waveform x of t, output is, let us say, z of t, which is directly proportional to the message signal M of t. Now let us look at the operation of the circuit. Okay, if you recall, the amplitude modulated signal will be like this for sinusoidal message signal. Then let me draw the carrier. The diode is like a half-wave rectifier. Okay, and what is the envelope? This is the envelope. Okay, let us say this one is your modulated signal. Okay, and this one is envelope of the modulated waveform. Now the diode will conduct look at the circuit. The diode will conduct only if it is forward biased. That means you can think of this action as some kind of rectification action. Recall from your electronic circuits, if you give a sine wave like this, then half a rectifier will give only positive half cycles like this. Okay, but more precisely we will see what is happening in this circuit. Okay, so obviously we only look at the positive half cycle of the carrier wave. So the output of this will be only the positive half cycle of the carrier wave like this. Negative half cycle will be completely removed because of the rectification action. Okay, so the negative half cycles cannot be make it forward biased. Therefore your signal looks like this. Okay, like this. So this is the output of the diode. Negative half cycles are removed by the diode. So we only need to understand what is happening during the positive half cycle of the carrier wave. No need to worry about the negative half cycle of the carrier wave. Okay, so let's say initially that this capacitor is uncharged. Okay, initially that this capacitor which you have at the output is completely without charge to start with. Initially, okay, to start with the capacitor doesn't have any charge. They don't have charge stored in it. So what will happen? Let me enlarge this figure. So it will be like this. I'm sorry. Oh, it will be like this. Now initially what happens? The capacitor starts to charge. It slowly charges. It follows the charge and reaches this point. Okay, as soon as it reaches this point, what will happen during the first positive half cycle of the carrier? Okay, that the circuit says in this circuit the resistor which is pretty large. If you look at this, the resistor is, let's say, pretty large. Therefore the charging takes place through the capacitor to the peak value. What is the peak value? This is the first peak value. So during the positive half cycle, in this half cycle, the capacitor charges to its peak value. Okay, peak value of the positive half cycle. Now as I said, initially the charge was 0, so it will charge like this. It starts from 0 and keep on charges and reaches the maximum value. Actually charging time constant will be very small because there is no resistor. So it charges through this path. Okay, through this path. So the charging time constant will be very small. Let us assume that to follow the carrier and the charge is like this. So let me erase this. Okay, so let me use green color. So it goes like this, charges and reaches this point. Okay, so it charges like this. It is going like charging path is like that. Now what is the voltage here? This point, maximum voltage. Similarly, during the trailing edge, the voltage tries to drops. That means this is my diode, and here I have capacitor. For the time being, let us forget about the resistor. Now this point is, let's say, P1, and what is the input side? Input side, it is slowly going down. So let's say this point, this voltage, let's say some V1. The input side is V1 and P1 is this one. Now P1 is greater than V1. Why? Because the voltage is going down. Okay, therefore in this portion, the diode will not conduct. The diode will off. So in this portion the diode, maybe same color I am using. In this yellow portion the diode will be off, because the anode potential, cathode potential will be larger than the anode potential. Okay, therefore the diode will be off, switched off, because it becomes reverse biased and it stops conducting. So if it stops conducting, what will happen? This diode will be open circuited. It will be open circuit like this. So the capacitor starts to discharge like this. The capacitor starts to discharge through the resistor like this. Okay, so that is discharging time constant RC. Okay, so the discharge phenomena will take place. So whatever the voltage stored across the capacitor, let's say P1 will start to decrease a little bit. So it starts to decrease like this, slowly decreases, depending on the time constant. Okay, let's say it discharges slowly like that. Okay, so this is the way it discharges. Now at this time, let's say T1, at this time the next positive half cycle comes again. This half cycle comes down. I show on the yellow color. Therefore again it starts to charge. It starts to charge and reaches the maximum value. Let's say P2, peak 2. Okay, and the diode conducts. So the diode from this point to, let's say this is V2 to P1, it conducts. Once it reaches the point P1, then the voltage is dropping, coming down. If the voltage is coming down, then what happens? The diode will be reverse biased. So in this region the diode will be reverse biased. So again the diode discharges slowly like this, and again it charges like this and reaches the next peak P3. The moment it reaches P3, then the cathode potential is higher than the anode potential, therefore the diode does not conduct, it stops conducting. So it slowly discharges like this, and by the time the next peak comes, it charges to next peak for P4, and again diode stops conducting, your capacitor starts to discharge and comes down like this, and this point again discharges like this, then charges P, then discharges, then charges to the peak value, then again discharges and goes like this, like that. So that is the operation takes place after the diode by using your capacitor and resistor. Okay, so it charges to the peak value and then again slowly discharges. During the discharge time, the resistance will come into the picture. So there will be some ripples which you can always remove by keeping a suitable low pass filter. So let me explain one more time, because this operation is little complicated. So let's say this is your envelope like this. So you have, let's say you have this waveform like that. Like this. Now remove these dotted lines. In fact, the dotted line will not be there. Okay, so just to draw the picture, I am drawing this. Oh, what you get is only the carrier. The carrier will be like this. In the beginning, when the positive half cycle comes, the diode conducts. Okay, so let me enlarge. The diode conducts like this. It starts slowly, conducts, therefore it charges the capacitor to the peak value P1, let's say P1. And if you assume that the charging circuit has a very small time constant, why is it very small time constant? During the positive direction when the diode conducts, it has very small resistance, forward resistance RF, and the capacitor like this. You may have some source resistance. Therefore, in the forward path, RS plus RF, very small resistance multiplied by C. So it charges quickly, okay, because of the very small time constant. Okay, so the capacitor voltage will more or less follow the carrier. So it follows the carrier like this and reaches the peak value. Okay, so this is what happening during the first half cycle. So you will keep on getting charge to the incoming voltage till it reaches the peak value P1. So when the capacitor reaches the peak value and when the input voltage drops, see the input voltage, I will show in the red line. Now the input voltage is dropping down. If the input voltage drops down, then what happens? The diode will be reverse biased, because this point, let me say A, and this point B. Because the point A is, let's say point B is at a higher voltage than point A. Okay, point A means this portion. Point B is at the potential of P1. So there is no conduction in the diode. The diode remains in the reverse biased during this falling portion. So this is my falling portion. Falling portion of the input. Okay, falling portion of the carrier half cycle. And during this period, during falling period, the capacitor discharges through the load resistance. Let me call this resistance as RL or simply R, no problem, load resistance. So in this, during discharge time, I am utilizing this R. During charge time, I will not go to the R, because R value generally I choose little high. Okay, and let's say there is certain discharge timing constant, and that discharge timing constant is RL times C. So how does it discharge? Let me draw in the yellow color. Slowly discharges like this. I have drawn in the yellow color. Okay, which is not too fast. Discharging is not too fast. Not too fast. So more or less it stays at a constant value. See, like this it stays constant value. Look at here. Okay, constant value, but it decays a little bit. It is not exactly constant, accurately constant, but it decays a little bit. That's why I put a small slanting line there. And then the next half cycle comes in, and at this point again it starts charging. It's charging like this. The capacitor starts charging and reaches the peak to value. When the capacitor voltage reaches this P2, again the diode becomes reverse biased. So let's say this point is small a and this point is P2. Between A to P2, the diode is forward biased. Once you reach the peak P2, the capacitor starts discharging because of the reverse biased condition. And therefore it slowly discharges. By the time the next half cycle comes, then it charges, reaches the P3 value. Again it slowly discharges. Then again it charges. This is charging portion, reaches the P4, peak 4, and slowly discharges like this. Okay, of course this diagram is highly exaggerated. Okay, exaggerated. Why? Because in real life you will not have like carrier like this. The carrier will be very, very close, like this, very, very close, like this, because high frequency, like this, not too far away. Okay, if you look at it, you cannot differentiate. The carrier will be very, very closely spaced. But this diagram is little or highly exaggerated. Okay, in the sense the carrier cycles will be much more closely spaced. See, the carrier cycles are very closely spaced. Therefore, it accurately follows the shape. Okay, so actually what you will see is not such a, this kind of envelope, okay, like rippled envelope, but fairly smooth envelope you will observe. Okay, so which can be smoothed if you want still further by a suitable low pass filter. Okay, so that is a basic principle of your envelope detector. You see, now the demodulator is very simple, extremely simple. You need only 3 components: diode, resistor and capacitor. Now one can ask a question, can I choose R value and C value arbitrarily? No, you cannot do that. So there are certain reasons that we will discuss now. Okay, so now for this to work, there are certain conditions. Okay, now let us look at the charging path. This is my diode and capacitor. So this is my charging path. The charging path, I have diode and capacitor. Let's say some resistance Rs you might associate with the input. Okay, so I have the input. That input has some resistor Rs. After all, the input is a voltage source, okay, coming from somewhere, maybe from, this is maybe from antenna, receiver antenna, and some front end receiver circuit, okay, or some previous stage of the same, some amplifier before to the demodulator. So there would be a source resistance Rs associated with the waveform x of t. And in the forward bias, the diode behaves like a simple resistor with a resistance of R suffix small f, or sometimes people write small r and small f. And here Rs is the source resistance and small rf forward bias resistance. Resistance of the diode. Typically both the Rs and R suffix f are of small values, very small value. Therefore, what will be the charging path? The charging path is this one. Though you have resistance RL, it will not take that path. There will not be any current flow. Okay, therefore the charging path is this one. And assuming that RL is sufficiently large, okay, this is much larger than your Rs and Rf. Okay, so we assume that RL is much greater than Rs plus Rf together, because in the charging path they are in series. Therefore, charging of C has a time constant which is given by Rs plus Rf times C. This is a time constant in the charging path. Now, what would you like this time constant to be? Should it be small or large? If it is large, then it will be a problem, because it will not charge very easily. It will take a lot of time to charge. By the time the next half cycle will come. So therefore, it should be extremely small. Extremely small. Therefore, whenever the cycle, the carrier wave comes, it charges quickly. Okay. Now we can quantify this. Then how small it should be? Okay, it should be much smaller than, let's say, cycle duration of the carrier wave. Okay, this is my carrier frequency. Carrier frequency. Let's say this is my sine wave, and now the duration is Tc. Okay, this your charging time constant Rs plus R times F times C should be much smaller than your time carrier wave period. So what is Tc? Tc is 1 by Fc. So 1 by Fc is much greater than Rs plus R suffix Rf times C. Otherwise, it will not follow the carrier soon. See, if you look at the figure, in the forward bias, we said it follows the carrier. See, let me draw the figure one more time. like this, you have the carrier. In the charging portion, it follows the carrier. See, it follows the carrier, reaches the peak, and discharges like this. Again, follows the carrier, okay, and reaches the peak. Then again discharges slowly. Again, it follows the carrier. Let me draw on the line. So in order to follow the carrier, the charging time constant should be very low. Otherwise, if it takes a large time constant, if it has large time constant, then what will happen? It will not charge like this, it will charge like this. Okay, so that's a problem. It is large charging time constant. There will be some lag. And this portion is small, extremely small time, small charging time constant. That's it. Okay, even if the resistant R is there, it will come in the parallel combination. Then also it will be less. Suppose let's say there is one more resistance R, and this R will come, RL will come in the parallel. Suppose you have two resistance parallel with a 3 ohm, then this will be less than 2 or 3. 2 less than 2. Therefore, still it will goes down. Okay, therefore don't worry about the load resistance. Okay, so therefore the point is that for the charging time constant, the condition that you should have is this one. Where did I write? Yeah, this is the condition for charging time constant that you should have. What is 1 by Fc? 1 by Fc is the time period of the carrier wave. The carrier wave is shown here. So it should be much smaller than 1 by Fc, so that the capacitor immediately charges the moment the diode starts to conduct. So it follows the half cycle of the carrier wave as it comes without any delay. So this is first condition. Okay, that means what? I cannot choose the capacitance value arbitrarily. If I choose very low value of the capacitance, then it will be a problem. It will not charge quickly. Okay, so this is the one. This is the condition that is required during the charging of the capacitor. Now the second thing is it has to discharge, right? So therefore we need one more condition. So the second condition is regarding discharge. I cannot discharge too fast and I cannot discharge too slowly. So now what is the discharge path? The discharge path is through the load resistance, like this. This is my discharge path. Therefore the capacitor discharges through RL. Now what is the discharging time constant? Discharging time constant is RL times C. Now what would you like this RLC be? Okay, should it be large value or small value? It should be large. Okay, so that it should discharge slowly. So RL times C should be large. How much large it should be? How large it should be? The condition says RL times C should be large, but it should be greater than 1 over Fc. Okay, this is one aspect. So this can lead to a situation which is not desirable sometimes. Let us look at the picture once again. I have drawn some, yeah. If it is very large, then what will happen? Maybe I'll draw the same figure one more time. Like this. Your half waves are like that. Now if the discharging time constant is very very large, then it slowly discharges. Then it charges to this point, it like this. Okay, then it discharges like that. It goes like this. It will not capture this peak and this peak. Okay, this is called clipping distortion. If you choose very large time discharging time constant, then what you will have something called clipping distortion. So this is due to large discharging time constant, RLC. Okay, let's say this is P1, P2, P3, P4 and P5. So therefore you miss P4 and P5 because you are discharging very slowly. Okay, suppose your discharging time constant is very large, this is what will happen. Okay, your capacitor will discharge very slowly. In case if it is too fast, then what will happen? It will come down like this. It will not follow the peak. Okay, capacitor will not follow those peaks, so we may lose. If it is too high, it will not follow the peak. Okay, so we may lose information. The demodulated waveform will not be the same as your message signal what you used for modulating the carrier. Okay, so very large value also very bad, you should not choose. Okay, because you are not following the envelope. So this will lead to a kind of clipping, that is you would miss the variations in between the peaks. Therefore the discharging time should not be so slow and it should not be so fast. Okay, so therefore this kind of distortion that will come up in the envelope, which you call clipping distortion, which you should avoid. So if you want to get a faithful reproduction, this is a term which we repeatedly use in communication, something called a faithful reproduction. Faithful reproduction of the envelope, then this time constant must be less than the what you call your time period of the carrier wave. Okay, and one more thing, it should be smaller than the rate at which the highest rate at which the message signal itself can vary. So the important condition is RL times C must be less than your highest frequency. What is the highest frequency? Recall from your spectrum of your message signal, M of F. The highest frequency that we said was B, right? Therefore this time constant must be smaller than 1 over B. Okay, so the modulated signal itself can vary. B is the highest rate of the message signal variation. Therefore this discharging time constant depends on the bandwidth of the message signal. So your RLC times much less than 1 over B. Okay, and this should be much higher than 1 over your carrier frequency. Okay, first condition, what did we say? This is the second condition. The first condition is RLC must be much higher than 1 over FC. If you combine these two conditions, then you can say RLC is much less than 1 over RLC is much higher than 1 over FC and much less than 1 over B. In between, if you choose your time constant, then you are safe. Okay, if these two conditions are satisfied, by and large we have a system which works nicely. Okay, so these are the two conditions that we need to satisfy. Okay, so that's all about the envelope detector. Now you can appreciate why the AM system is used at the expense of 33.33% of efficiency. Okay, and this circuit, this detector circuit is called a diode detector. So you can call it by envelope detector or diode detector. So as you see, this has only three components: the diode, the capacitor and the resistor. That's it. It is a very simple circuit. This is what most of your AM receivers would do. Okay, so that's all about envelope detector. Okay, so in the next lecture we will discuss a simple example. Okay, so let me stop. Thank you very much.